next part of this weak acid titration is to add more strong base to it. First, the reaction between acid and base, again, because it's a strong base being added, is going to go to completion. Again, I'm going to write the acid just as HA for ease of writing, but it's acetic acid. And so I'm going to get water when the hydroxide pulls hydrogens off of that acid, leaving a conjugate base. Next step, how much weak acid and strong base are we starting with? So we are going to be starting with the same amount of weak acid that we've been starting with in our other problems, which was 0.005. I write that down. And for the base, we are going to be adding 25 milliliters, so this is for the NaOH. I'm going to be adding 25 mils, or 0.025 liters, with a concentration of 0.1 mole. And I will solve for X, and I will get 0.0025 moles of hydroxide. So that's how much I start with here. Not concerned about the water, and I don't start with any of the conjugate base. Then the change, what's the limiting reactant? The base, 0.0025 minus 0.0025. Don't worry about the water, and I'm going to be making 0.0025 of my conjugate base. So now my ending amount, I'm just going to write down here, is going to be 0.0025 of the acid, none of the strong base, but 0.0025 of the conjugate base. And so I'm going to have the same amount of each of these, of the weak acid and the conjugate base. So when I have my weak acid equilibrium, and I put that in for my, put those values in for my initial amounts, because after this reaction takes place, the weak acid and its conjugate base are going to try to find this new equilibrium position. I have 0.0025 here, none of this, and 0.0025 of that. And you'll see that that is the same as the end point from the last reaction. The change, it's going to find a new equilibrium. We don't know exactly where that's going to be, so we are going to put our x's in there, and the equilibrium amount, 0.0025 minus x. This is plus x, 0.0025 plus x. So my Ka expression, products over reactants raised to their coefficients, I have x times 0.0025 plus x over 0.0025 minus x, equal to our Ka value, which is 1.8 times 10 to the negative fifth. And when I solve this, I'm going to say that the x is much, much smaller than the 0.0025. 0.0025 can reduce out, and I find out that my x is equal to my Ka, or 1.8 times 10 to the negative fifth. Another mathematical expression that would relate to this is the pH is equal to the pKa. This particular point is called the half equivalence point because I have half the amount of, how do I want to say this? Half of my stuff is in the acid form and half of it is in the conjugate base form. And so my pKa and my pH will be equal to each other because those two amounts are the same. So when I find pH, I'm just going to take negative log of the pKa, and I get an answer of 4.74. The next problem, we are going to add a little bit more base. We're going to be adding 50 mils of NaOH to the 50 mils of acetic acid, and this is the point in the strong titration where we reached a pH of 7. You will find out in this problem you are not going to reach a pH of 7 even though you have the same amount of acid and base in your mixture. The pH will not be 7 because of this weak acid and its properties. Where the strong acid broke up 100%, the weak acid does not, and we are going to look at how that affects things. So the next one, it's the same reaction, believe it or not. We're going to have weak acid reacting with hydroxide, going 100% to form water and the anion. I have my starting amounts. Again, for my weak acid, it's 0.005, and because it's 50 mils of the same concentration, the hydroxide will also be 0.005. Don't worry about the water, and I have no conjugate base to start. Here I don't have a limiting reactant. They are both equal, so my change is going to be 0.005, and so I will end up 0.005 here. I will end up with none of this and none of this, and a 0.005 of a conjugate base. And that is why the pH is not going to be 7, because I have base present in my solution. So now I have this new equilibrium position that this conjugate base, which remember, A minus is C2H3O2 minus. This C2H3O2 minus will find some hydrogens in the water to take, because it likes to be with hydrogen. That's what a weak acid is. It likes to have hydrogen with its anion, and so the A minus here, the acetate ion, will be in water, and it will find some hydrogens from that water to react with or take and form the weak acid, acetic acid, and leave hydroxides in the water. So now I have an actual equilibrium reaction. This was 100%. This is equilibrium. And so I make an actual ice table. This is an Isend table. And my starting amount here is 0.005. I don't worry about the water. I have none of this and none of this. Some of these ions are going to take hydrogens from the water. Don't know how many, so we say X amount. 0.005 minus X, and then plus X plus X. Now it says write the Ka expression and solve a weak acid problem. Well, this isn't a weak acid. This is a weak base, and it's taking hydrogens away. Well, can I find the Kb with the known Ka? And the answer, absolutely. Ka times Kb is equal to Kw. I know the Ka is 1.8 times 10 to the negative fifth. I need the Kb for this conjugate base of acetic acid. Kw is 1 times 10 to the negative 14th. So to solve for Kb, I divide by 1.8 times 10 to the negative fifth on both sides, and I find out the Kb is 5.56 times 10 to the negative 10th. So now my Kb expression, similar to the Ka expression, Kb is equal to products, x squared, over reactants, 0.005 minus x, and we're going to say x is much, much smaller, and so that Kb is 5.56 times 10 to the negative 10th. When I solve for x, I get 1.67 times 10 to the negative fifth. What does x represent? I go back up into my reaction. I find out it represents my hydroxide ion concentration. So I can find the POH, taking the negative log of that, and I find the POH to be 4.78. pH then 14 minus that, because of that pH-POH relationship, and I will get 9.22 for that pH. And as you see, it's not a pH of 7, it's a basic pH, because we end up having conjugate base in our reaction. One last part, I believe. Now we are going past that equivalence point and adding 60 mils. Again, we're going to go through the same process. If you do it enough times, it's going to stick in your head more than you want it to. So we are going to have a reaction going 100%, leaving some conjugate base. I'm starting with an initial amount that's been the same the whole time, 0.005. But now my hydroxide amount, 60 mils at 0.1, is 0.006. Don't worry about the water, none of that. Now my limiting reactant is the weak acid. I have less of that than the hydroxide, 0.005. And so I will make this much conjugate base. And so my end, no weak acid, a little bit of strong base, and more weak base. So now I have a little bit of weak base that's going to take some hydrogens and leave some hydroxide, but compared to my strong base, really no effect. If I have this much strong base compared to my amount of weak base, there's not going to be that many weak base ions that are going to take hydrogens off of the water. So this is what's going to affect the pH. And so now I don't need to write a Ka or a Kb expression because I have strong base in there. And so to finish this off, if I know POH is equal to negative log hydroxide ion concentration, remember this is moles of hydroxide, I have to get that to concentration, which is moles over total volume, which was 50 mils plus 60 mils, or 0.05 plus 0.06 milliliters. 60 and 50, have to have those in liters. I will get a POH of 2.04. Just a sidebar, if you calculated this, you should get about 0.0091 for just that part inside. So 2.04 is the POH. Now if I want to find the pH, 14 minus that, and the pH is 11.96. If you have strong base in a mixture with weak base, the strong base is going to have the largest effect on the pH. That is all. Good luck.